Hi, everyone. Thanks for joining us. We're just going to wait a few more minutes here. All right, I think we can get started if you are ready to go, Heather. So I'm happy to introduce our seminar speaker this week, Dr. Heather Roman-Stork. Dr. Roman-Stork is an ocean scientist and researcher at NOAA STAR and the Satellite Oceanography and Climatology Division, working on global eddy tracking. She received her bachelor's in environmental geoscience from Boston College in 2016, her master's in meteorology from Florida State University in 2018, and her PhD in marine science from the University of South Carolina in 2020. During her PhD, she received the NASA South Carolina Space Grant Consortium Graduate Research Fellowship. Her research interests include tracking and monitoring of mesoscale systems from satellite observations, developing operational oceanographic data sets, monsoon dynamics, tropical climatology, and air-sea interactions. So today she will speak to us about analyzing the impact of intraseasonal oscillations on Indian monsoon variability. Take it away, Heather.
All right, good morning or afternoon, everyone. For me, it's afternoon. Thank you for coming here today virtually. And to start off, I'd like to thank Dr. Frank Bryan for inviting me to give this talk, and also to Katie and Tracy for arranging this talk. So thank you for the lovely introduction. And I'll go ahead and get started on my talk, analyzing the impact of intraseasonal oscillations on Indian monsoon variability. So there are a number of motivators for this talk and my research. As previously mentioned, a lot of my research interests involve mesoscale systems and also monsoon dynamics and tropical dynamics. So the southwest monsoon, which is part of the overall Indian monsoon system, which I'll get into in a minute, is a highly dynamic system. It's air-sea coupled and directly impacts the lives of over 1 billion people. It impacts the global economy. So it's a really important system to understand, not just from a meteorological or oceanographic point of view or a climate point of view, but also from a human point of view and an economic point of view. For more of the climate and modeling aspect of this, the Indian monsoon system is actually the largest source of diabatic heating in the upper atmosphere. So it's really important that we understand the processes that contribute to this Indian monsoon system and how it varies through time, both on long-term scales and also on short-term synoptic timescales and intraseasonal timescales. So what we wanted to do with this research is explore the impacts and controls that influence monsoon onset and intraseasonal variability. So that's more subseasonal, less than 90-day variability. So to sort of break this down, we wanted to see how these intraseasonal oscillations, or ISOs, impact monsoon rainfall and modulate the active and break phases of the monsoon. So phases of these monsoons that have more precipitation or less precipitation and lead to droughts and floods. I also wanted to explore how freshwater input from the Bay of Bengal into the southeastern Arabian Sea drives monsoon onset and strength. So I'll get to the processes that influence this in a little bit, but there's some really interesting dynamics involved with that. The Bay of Bengal and southeastern Arabian Sea actually experience a lot of tropical cyclone activity. So I wanted to see how these TCs interact with ISOs and the monsoon trough to influence monsoon onset, variability, and strength, and how these also can feed back into ISO strength. And then finally, and this is more related to my current work with the Lab for Satellite Altimetry at NOAA, I want to explore how mesoscale eddies play a role in the general circulation and air-sea interactions, specifically in the Bay of Bengal, but then how these mesoscale systems feed back into atmospheric convection and monsoon strength. So accordingly, the outline for this talk is going to be in 4 parts. So first, I'll explore the role of salinity in determining monsoon onset and variability. Then I'll look at how tropical cyclone and intraseasonal oscillation interactions in the Indian Ocean occur. And then intraseasonal oscillations in the Indian Ocean. And then finally, I'll end with eddy variability and connections to atmospheric convection in the Bay of Bengal. So it'll be sort of a survey of my research overall. So for those of you who are perhaps less familiar with the Indian Ocean or just haven't worked with it in a while, it's actually a very interesting basin to work with, at least from my standpoint, because everything is seasonally reversing. So for half the year, you have all of the currents and winds moving in one direction, and then all of that flips for the other half of the year. So the Indian monsoon system has 2 different monsoons that dictate basically how these winds and currents operate. So the southwest monsoon, which is what we refer to as the Indian summer monsoon or just the Indian monsoon in general, that's the more famous one that most people are familiar with. That occurs in climatology from June through September, and that's what I'll mainly be focusing on today. Then there's also the northeast monsoon, which occurs from November to February. And all of these are defined by the direction of winds over India. So for the southwest monsoon, you'll have winds coming out of the southwest over India. And then of course, for the northeast monsoon, you'll have winds out of the northeast over India. And when I'll be describing southwest monsoon onset, that occurs in climatology over the southwestern state of Kerala. So where this teal star is, that's roughly where Kerala is. So when I talk about monsoon onset or the monsoon onset vortex moving over Kerala, that's geographically where I mean. And while the overall Indian Ocean is of great importance and is a really interesting place to work, most of the research I'll be describing today will occur mostly in the northern Indian Ocean, specifically in the Bay of Bengal and the southeastern Arabian Sea. So monsoon onset obviously is a significant interest of mine, specifically how monsoon onset impacts the strong, weak, and normal phases of the monsoon. So here I've got a figure that shows the difference in total precipitation between a weaker, a stronger, and basically the difference between a weaker and a stronger monsoon, and also the difference between the two. So while there's roughly 900 millimeters in climatology of precipitation associated with the southwest monsoon in general, it does vary by about plus or minus 10%. And you can see that that ends up having a fairly significant change in precipitation overall. So you can see the differences over sort of north central India and then over the Bay of Bengal, and then along this Arabian Sea coast here. So there's a lot of differences in precipitation associated with different monsoon regimes, and it's really important to forecast these, not just for day-to-day well-being in life, but also for agriculture and local economy and things like that. So 2019 was of particular interest to me because it was the first strong monsoon since 1994. So we had a lot of normal monsoons and really weak monsoons before that. But 2019 was the first really strong monsoon. And it actually had sort of an interesting onset in that it was delayed by about a week, which is pretty late in terms of monsoon onset variability there. So I started this movie a little early, but if you can see, the monsoon onset vortex actually formed over the southeastern Arabian Sea and then moved north along the coast, hitting Kerala around June 8th, June 9th, and then propagating northward along the coast. And that's generally how monsoon onset occurs. And of course, the southwest monsoon isn't just one big storm cloud that sits over the subcontinent for a few months and then dissipates. It's actually a combination of multiple different systems and intraseasonal oscillations that in total end up contributing to the total monsoon rainfall. And these active and break cycles of the monsoon are going to be largely controlled by these ISOs and are major importance for forecasting or major interest to a lot of researchers. So that's mainly what we're going to be focusing on today. So I've discussed a little bit about strong and weak monsoons. So this is basically set forward by IITM, where a strong monsoon is 10% above this long-term mean from 1871 to 2017. So working with the Southwest monsoon is really nice in that we have a quote-unquote long-term record. I did paleoclimate, so long-term has sort of a different meaning, but in a meteorological sense, 1871 to present is a really long-term meteorological record to have. So the strong monsoons are about 10% above this long-term mean, and weak monsoons are 10% below that long-term mean. As I mentioned before, 2019 was the first strong monsoon we had since 1994. So actually a major motivator for my research was to figure out why we had this 25-year-long drought in strong monsoons, pretty much. For those of you who are curious, 2020 was almost a strong monsoon. I believe it was like 9.9 or 9.8% above the long-term mean. And then in terms of controls for monsoon rainfall and monsoon strength, we also have the Indian Ocean Dipole, or IOD, and the El Nino Southern Oscillation, or ENSO, which help modulate monsoon strength and variability. I'll get to that a little bit later. So one of the other things that really interests me, and that is going to be really important in this research, is the freshwater exchange between the Arabian Sea and the Bay of Bengal. So you can see from this diagram, this movie here of S-map satellite salinity. The Arabian Sea is a really, really dry basin. It's highly evaporation dominated, it's highly saline. By contrast, the Bay of Bengal is a comparatively fresh basin. There's a lot of riverine input from a lot of really large river systems. Some of the largest river systems in the world enter into the Bay of, basically dump the water, fresh water into the Bay of Bengal. So you have, with these seasonally reversing currents, you have a really strong salinity gradient between the two of them. So during the northeast monsoon, you have the East India Coastal Current, or the AICC, which will transport this really fresh water from the Bay of Bengal around Sri Lanka and the tip of India into the southeastern Arabian Sea. That'll actually create a fresh pool, and I'll get to that in a little bit, but that's going to be really important for monsoon onset. And then during the southwest monsoon, you have the West India Coastal Current, or WICC, and the East India Coastal Current transporting this highly saline water from the Arabian Sea, again, around the tip of India and Sri Lanka, into the Bay of Bengal. So this exchange of salt and fresh water is going to be really important, not only for mixed layer dynamics in the Bay of Bengal, but also for monsoon onset and variability. So that leads into my first subject here, which is going to be the role of salinity in determining southwest monsoon onset and variability. So as I mentioned before, this salinity exchange is really important for southwest monsoon onset. And the conventional wisdom for how southwest monsoon onset occurs really starts back in October of the previous year. So as I mentioned, in climatology, the southwest monsoon occurs around June 1st. So the beginning of southwest monsoon onset actually really occurs in October, where you have this fresh water from the Bay of Bengal that gets transported by the East India Coastal Current and modulated actually by coastal Kelvin wave propagation around the Bay of Bengal, and by January, you should have this low salinity plume that moves around Sri Lanka and the tip of India and gets guided into the southeastern Arabian Sea by this feature called the Lakshadweep High. And the strength and proximity to the coast of this anticyclonic circulation will really help guide this fresh water into the southeastern Arabian Sea, or seas region. And how big that fresh pool ends up being and how close it is to the coast will help determine how big this fresh pool is, and will help create the conditions necessary for high SSTs in the Arabian Sea mini warm pool to form. That mini warm pool will then help generate the monsoon onset vortex, and then around June 1st, you have monsoon onset. And that's really the conventional wisdom for how monsoon onset occurs, for those of you who are less familiar with this. But we wanted to figure out how this freshwater transport is going to really impact the timing and strength of monsoon onset overall. So to do this, we first wanted to explore which sea surface salinity products to investigate. So we're looking at surface fluxes and salinity in freshwater, So we looked at 2 ocean reanalyses, Argo floats, and then the 3 available satellite salinity products. And part of this is due to the depth of the first layer in the models in Argo versus the skin deep measurements of satellite salinity. But you can see from this Taylor diagram that actually all of the products come pretty close with one another statistically in terms of monitoring this freshwater transport into the southeastern Arabian Sea. But ultimately what we ended up deciding is that ORAS-5 ocean reanalysis and satellite salinity products were going to be more reliable just for their higher resolution and for measuring skin basically skin values in the seas region. So what we then wanted to do is analyze the barrier layer development in the seas. So this difference between the mixed layer depth and isothermal layer depth, which will ultimately prevent entrainment cooling and allow for the development of this Arabian Sea mini warm pool. So what we did is we analyzed all data from 1980 to 2016 and created composite strong, weak, and normal monsoon years. Then we analyzed with depth what the salinity and temperature profiles looked like and how the barrier layer developed across these composite years. So what we found is that for strong monsoons, we actually have a much weaker fresh pool across both SODA and ORAS-5 reanalysis, which was pretty much contrary to what we had expected. We expected much deeper, more resilient fresh pool, which would in theory lead to a higher temperatures in the Arabian Sea mini warm pool, and then of course a stronger monsoon onset. But that's not really what we're seeing here. We actually have a shallower barrier layer leading into a stronger monsoon, and we have a weaker fresh pool. By contrast, for the weak monsoon years in both models, we had a much deeper barrier layer by about 5 meters, and we actually had a much stronger fresh pool in both normal and weak monsoon years. So we wanted to explore why this was occurring. So this was really in contrast to what the conventional wisdom had been so far. So to do this, what we did is we constructed a mixed layer salt budget with our composite monsoon years for this southeastern Arabian Sea region. And what we found is that surface freshwater fluxes varied slightly, which one might expect, especially because surface freshwater fluxes are directly related to precipitation, so it's perhaps not much of a surprise that there's more precipitation during a strong monsoon. But where the main differences really occurred were in these zonal and meridional advection terms, especially the zonal advection terms. So you can see in the months leading up to monsoon onset, the zonal advection term for a strong monsoon was actually much stronger in the eastward direction, in the westward direction than a normal and a weak monsoon year. So we wanted to explore then what was causing this and what currents were contributing to this zonal advection that was causing such a discrepancy between terms. So to do this, we calculated surface freshwater fluxes, again from our composite strong, weak, and normal monsoon years from left to right. And what we can see is that in the months leading up to monsoon onset, it's actually not the East India coastal current or the West India coastal current, which are really those meridional advection terms, but instead it's the North Equatorial current, or the NEC, that's actually going to vary the most significantly between monsoon regimes. So you can see this especially in February and April, that we have a much, much stronger NEC being transported in the negative or westward direction during a strong monsoon versus a weak and normal monsoon. And it's actually much more persistent. So you can see in April of a strong monsoon regime, we still have these really high NEC flux values compared to the other monsoon regimes. And that's really what's going to be responsible for these shallower barrier layers that are actually extended over a longer period of time. So while during a weak or a normal monsoon regime, you have stronger meridional values, that's actually going to help guide these freshwater fluxes closer to the coast, and they'll move farther north, but again, they'll be more confined to the coast. So you'll have a smaller Arabian Sea mini warm pool. It'll just be more intense in a very small area versus during a strong monsoon, it'll be more spread out and shallower, but it'll be persistent for a lot longer, which will allow for a stronger monsoon onset. We can see this in mixed layer parameters as well. So ocean heat content actually doesn't vary that much across monsoon regimes, but we can see barrier layer thickness is much higher during a weak or a normal monsoon regime versus our strong monsoon regimes. And then of course we can see our surface moisture flux values where we have much more evaporation leading into a strong monsoon, and then of course more precipitation during a strong monsoon. And then leading into a weak monsoon, you have a little bit more precipitation before the monsoon occurs. Now, looking at trends, again, we wanted to see why we hadn't seen a strong monsoon since 1994. So in this figure, we have trends in moisture flux, meridional freshwater transport, mixed layer depth anomalies, barrier layer thickness anomalies, and in upper ocean heat content anomalies. And our weak monsoons are going to be shaded in red, and our strong monsoons are going to be shaded in blue. And as you can see, there's no strong monsoons because this ends in 2016. So what we found is that moisture flux and barrier layer thickness actually both decreased substantially following 1994. So you can see, especially in moisture flux, that nothing's really happening in these trends until you reach roughly 1994, and then all of a sudden it drops off substantially. Then we also see barrier layer thickness. There's an oscillation to it, but it decreased substantially after 1994 as well. And then ocean heat content has, of course, been steadily increasing since really it starts picking up in the 90s, but the trend has existed throughout this record that we had here. So you can see that there's a pretty long-term trend in ocean heat content, which, of course, is related to warming oceans overall. So this led us to conclude that basically these upper ocean parameters, specifically moisture flux and barrier layer thickness, and how they've been changing through time, have really influenced monsoon onset overall, and not just monsoon onset, but monsoon strength overall. So shifting gears a little bit, I'm going to discuss how tropical cyclones and interseasonal oscillations in the Indian Ocean are related to one another, and actually how they impacted the 2020 monsoon onset. So 2020 was interesting for a lot of years. For me, one of the reasons it was interesting was because of Cyclone Amphan, which occurred in May of 2020 in the Bay of Bengal. So it really formed in mid-May, around May 15th in the southern Bay of Bengal, and then propagated almost meridionally into the northern Bay of Bengal. It reached a minimum central pressure around 909 millibars, I believe, and it actually reached what we would categorize as a Category 5 hurricane. It created a lot of devastation and was a horrible storm overall. But from a scientific standpoint and oceanographic standpoint, very interesting dynamics involved with it. So you can see just from this ocean colored figure here, the difference before and after Cyclone Amphan. The Bay of Bengal overall is pretty anoxic. There's not a lot of productivity, especially in the central Bay of Bengal. And you can see that there are a lot of phytoplankton blooms immediately following the storm. So it was a really interesting storm, had a huge impact on the Bay of Bengal. And I wanted to see what dynamics occurred to really cause this storm and why it was so devastating. So in my investigation into this, I plotted precipitation, sea level anomalies, sea surface temperature, and sea surface salinity. So for those of you who are familiar with sea level anomalies, you can see that right as Cyclone Amphan was forming, there was an equatorial Kelvin wave that arrived near the Bay of Bengal. And I saw this and I was so excited because I love Kelvin waves. And I wanted to see how this Kelvin wave impacted Amphan's genesis and what atmospheric processes were being impacted by this overall. So I also wanted to see how it impacted the Bay of Bengal. So this is a depth transect along pretty much the northern section of Amphan's trajectory in the Bay of Bengal. And you can see that we have really low salinity values and high temperatures leading up to Amphan. And then you can tell pretty much when Amphan reached its minimum central pressure here, because we have a huge increase in mixed layer depth. So we've got about a 10-meter increase in mixed layer depth. And since the Bay of Bengal already has really, really shallow mixed layers, a 10-meter increase has almost doubled the mixed layer there. So that's a pretty substantial impact. We also had a decrease of about 2 PSU to depth. in temperature and an increase in salinity overall. So it had a pretty interesting impact on the Bay of Bengal overall, pretty substantial impact, and it was highly air-sea coupled, as we will see in a moment. So I'm sure many of you are familiar with the Madden-Julian oscillation, especially since I stole this graphic from UCAR. So for those of you who are maybe a little less familiar with it, the Madden-Julian oscillation is the most famous of the ISOs. It's also the most dominant. It has a 30-90-day spectral peak for when it occurs and a wavelength of about 10,000 kilometers. It is eastward propagating and equatorially trapped for the most part. And it has a lot of impacts on the Indian Ocean overall, with this alternating pattern of convection and precipitation, and its northward propagating boreal summer intraseasonal oscillation, or BSISO, which is related to the MJO, that can propagate through the Bay of Bengal and have some pretty devastating impacts, and also significantly impact the active and break cycles of the monsoon. And for our purposes, what's also really interesting about the MJO is that can help trigger both monsoon onset and cyclogenesis, both of which were the case in 2020. So I wanted to see how the MJO and that coastal Kelvin wave, I was talking about coastal Kelvin wave, equatorial Kelvin wave earlier, were related to one another and how they impacted both southwest monsoon onset, because if you'll recall, Amphan occurred from pretty much the middle of May to the end of May. So it had an impact on monsoon onset, and then how the MJO, Amphan, and onset were all related to one another. So to do this, I looked at unfiltered and then 30 and 90-day filtered precipitation, sea level anomalies, sea surface temperatures, and sea surface salinity. So this is in the Bay of Bengal. So this is from April to the end of May, where monsoon onset occurred pretty much right here, because in 2020 it occurred with climatology. So you can see where Amphan forms. It was near equatorial, but of course not quite equatorial because it was a hurricane. And you can see how it propagated almost meridionally over a space of about a week. You can see our coastal Kelvin wave, our equatorial Kelvin wave did hit the coast and become a coastal Kelvin wave. And then you can see, of course, the temperature change following the storm. But when we filter this for the MJO wavelength, what we can see is that, yes, the MJO did in fact have a pretty significant impact. You can see these alternating bands of MJO strength moving here and how that impacted Amphan's formation. Now, if we move into the Southeastern Arabian Sea region, we can actually see a pretty similar pattern forming here, and actually a much stronger MJO signal, or more pronounced signal, I suppose I should say. So you can see that the northward propagating part of the MJO actually did move into the Southeastern Arabian Sea and have a pretty significant impact on the Southeastern Arabian Sea overall. And we do see this MJO signal as it propagated eastward from the Southeastern Arabian Sea into the Bay of Bengal overall. So we can see this really if we make spatial plots as well. So I apologize that the text is kind of tiny, but these first two rows are pretty much leading into Amphan's formation. So we have May 14th through the 19th, and then this bottom row here is monsoon onset. So what pretty much happened is that the Madden-Julian oscillation and boreal summer intraseasonal oscillation passed through the equatorial Indian Ocean around mid-May. And this helped basically set up the low-level westerlies in the Southeastern Arabian Sea that led to monsoon onset, and actually also contributed a significant amount of moisture to the Southeastern Arabian Sea in the process. So if you look at this time series of freshwater flux on the bottom here, you can actually see that the spike for for moisture flux associated with Amphan and this the MJO signal was actually more substantial than monsoon onset overall. So the peak in moisture flux was actually higher from this TC and from this ISO than from monsoon onset, which is supposed to be the major spike in moisture that occurs at this time. So we had the MJO and this boreal summer intraseasonal oscillation in the seas, and then as Amphan spun up, that also helped contribute moisture and impact the low-level winds in the region as well. So really we have this interplay of the MJO, boreal summer intraseasonal oscillation, a tropical cyclone, and monsoon onset, all influencing one another at the same time to help pretty much set up monsoon onset occurring with climatology. And actually, I'll get into this a little in a little while, but because of the conditions in 2019 with the Indian Ocean dipole, we actually should have had a delayed monsoon onset, but because of these storms and because of the MJO, we actually had a climatological onset instead. So really important processes and a very interesting monsoon onset, which was par for the course for a very interesting year. So I've discussed the MJO pretty in depth already, but a lot of my research has been involving intraseasonal oscillations in the Indian Ocean, and the two I'm going to be focusing on are the MJO and the Quasibiweekly oscillation. So there are a lot of different intraseasonal oscillations at play in the Indian Ocean and involved with monsoon variability. So there are 3 to 7 day synoptic oscillations. We have the boreal summer oscillation, which is on 2 different time scales, the 15 to 30 day and 30 to 60 day. But the two I'm mainly going to be focusing on are, again, the 30 to 90 day Madden-Julian oscillation and the 10 to 20 day Quasibiweekly oscillation. So I've showed the slide already, but again, the MJO is equatorially trapped and characterized by these eastward propagating bands of positive and negative OLR or convection. So we wanted to see how these intraseasonal oscillations are reflected in ocean parameters and how we can use satellite observations of surface oceanographic parameters to really monitor these processes. So what we did is we took composites of Madden-Julian oscillation in sea surface salinity and sea level anomalies, and we filtered them for the MJO wavelength. So what we can see is not necessarily the actual convection associated with the Madden-Julian oscillation, but what we can see instead are the Kelvin and Rossby waves associated with the MJO that help trigger, many believe, help trigger these MJO events, and which are associated with the MJO events in the ocean. So we can actually see these alternating bands and how they propagate through time. In sea surface salinity, we really don't see the planetary waves. Instead, what we see is that the strongest sea surface salinity signals are actually around the maritime continent and more associated with the suppressed phase of MJO convection. So just in the Indian Ocean, what we can do is we can also look at Havmiller diagrams of these parameters. And if we look at precipitation, sea surface salinity, sea level anomalies, we can see again that sea surface salinity more clearly follows the actual patterns of precipitation. So you can see the eastward and northward propagation of the systems. It just has a delay, and it's more associated with the currents and the negative phase of the MJO that are going to be reflected in sea surface salinity. In sea level anomalies, again, we're more going to be seeing planetary wave propagation. So you can see this is especially along the coast. You can see how these Kelvin waves are propagating, and you can see the equatorially trapped waves as well. So the Quasibiweekly oscillation is what I did my master's on. It is a topic that's close to my heart. And it's also sort of the ugly stepsister of ISOs. Not a lot of people study it, but I'm here to convince you that everyone should care and we should all study it. So unlike the MJO, it's not equatorially trapped. It consists of a double cell structure where one is centered around, mostly in the Bay of Bengal. The northern cell is centered around 15 to 20 degrees north in the Bay of Bengal, and the other one is centered roughly around the equator. And these double cell structures basically phase trapped with one another, where the southern cell, as we'll discuss in a little while, is actually going to be generated by a mixed Rossby gravity wave in sort of this equatorial Bay of Bengal region. And the northern cell is triggered by a breaking Rossby wave in the upper atmosphere that propagates out of the North Pacific and South China Sea. So this whole system, once it becomes phase locked with one another, is westward propagating out of the Bay of Bengal and moves over India before dissipating over India and the Arabian Sea. So it's actually has pretty significant impacts on the active and break cycles in the monsoon, and has a significant impact on the Bay of Bengal as well. So we did the same thing as we did with the MJO, and we really wanted to look at how the Indian Ocean and Bay of Bengal really respond to these quasi-biweekly oscillations. And again, what we found mainly was that this mixed Rossby gravity wave in the equatorial Indian Ocean actually acts as a precursor for the southern cell of the double cell structure and actually helps trigger the atmospheric convection associated with this double cell. We don't really see a strong signal associated with the northern cell, although there is some coastal Kelvin wave modulation that it does occur. In SMAP sea surface salinity, again, we don't have a really strong signal associated with it. What we do see is that in the Bay of Bengal, we do have a fairly strong upwelling signal in this response to the planetary waves that occur there as well. So if we then shift our focus more to the Bay of Bengal, since it is, unlike the MJO, it doesn't have sweeping implications for both the Indian Ocean and Pacific Ocean, and doesn't influence global weather and climate. The quasi-biweekly oscillation does have significant impacts, however, on the Bay of Bengal. So this is using the NEMO ocean model and NASA JAXA GPM precipitation. So if we look at composites of these variables in the Bay of Bengal, what we can actually see is that the mixed layer depth will increase substantially in response to the northern cell propagating through the Bay of Bengal. And we can also see a pretty strong upwelling signal in the central Bay of Bengal where precipitation was strongest through these composite years. So we have an overall cooling effect and an overall salinification associated with these systems. We can see that a little bit with these Hofmüller diagrams. So this is just for the northern cell of the system. You can see that westward propagation and that sort of sinusoidal pattern associated with precipitation. But again, you can mostly see that the response of these storms is, of these systems is pretty much restricted to the central Bay of Bengal, where we have that upwelling system, and then to the coast of the Bay of Bengal, where this coastal Kelvin wave modulation occurs. So I wanted to see how this also impacts upwelling and productivity overall. So this is in composite days. So we have 7 days before the peak in precipitation, 7 days afterward. So in black, we have our peak of precipitation. Then we can see actually several days following the peak of precipitation is where we get our peak in Ekman pumping. This is calculated from CCMP winds. And then after we get our peak in Ekman pumping, several days later, we have our phytoplankton blooms and our increase in productivity overall associated with these systems. So we also want to see how deep into the Bay of Bengal this atmospheric signal can penetrate. So we looked, this is again using NEMO. We looked at temperature and salinity in different regions of the Bay of Bengal, because the Bay of Bengal responds very differently depending on the region. So the northern and central Bay of Bengal is going to be more dominated by riverine processes, whereas the southern equatorial Bay of Bengal is going to be more dominated by this salinity exchange between the Bay of Bengal and Arabian Sea. So what we wanted to see is how deep into the Bay of Bengal do these systems penetrate. What we can see is that since the northern Bay of Bengal is more riverine dominated, the 10 to 20 day signal is really more trapped above the thermocline here. So you can see, especially in salinity, that you're really only seeing surface variability. It's not really going past 50 meters overall. But in the southern and equatorial Bay of Bengal, we actually have a much higher signal at depth than at the surface. And that was sort of surprising. So what we actually see is that it's below the mixed layer where it's really thermocline variability that we're seeing. So we're seeing 10 to 20 day oscillations translated to the thermocline that are going to have the strongest signal rather than just surface variability and upwelling. So this leads into more of my recent work. slightly related to my recent work, which is eddy variability and convection in connections to atmospheric convection in the Bay of Bengal, specifically mesoscale eddy variability. So I've talked a little bit about coastal Kelvin waves in the Bay of Bengal. So there are four major coastal Kelvin waves in the Bay of Bengal. There are 2 upwelling and 2 downwelling. The one that we care about in terms of eddy variability in the Bay of Bengal is going to be the second downwelling Kelvin wave. And that arrives in roughly October through November. So if October sounds familiar, it's because this coastal Kelvin wave is actually the strongest one. And that's actually going to help modulate the amount of fresh water that is transported by the East India coastal current into the southeastern Arabian Sea. And it's going to be this coastal Kelvin wave that also impacts monsoon onset overall and that amount of fresh water that's transported. So everything's connected in Bay of Bengal and southeastern Arabian Sea. So this Kelvin wave also radiates Rossby waves that help trigger eddying in this East India coastal current region. So it was really important to us that we understand how the Indian Ocean dipole and the El Nino Southern Oscillation impact this this coastal Kelvin wave and Rossby wave variability in the Bay of Bengal, and how that impacts not just monsoon onset overall, but also mesoscale eddy variability, and how these eddies then feed back into atmospheric convection to impact monsoon strength that year. So that was sort of the goal of this study. So what we did is we did mesoscale eddy tracking on 25 years of daily altimetric observations in the Bay of Bengal. So from 1993 through 2018, we found all mesoscale eddies in the Bay of Bengal at this time and analyzed their characteristics and trajectories. So this is divided up by anticyclonic eddies, or AEs, and cyclonic eddies, CEs. And then the number of eddies, the radius of the eddies, their eddy amplitude, the EKE associated with them, and then of course, where the most eddies were generated in which region of the Bay of Bengal. So as I mentioned before, the Bay of Bengal is really, has a lot of meridional variability associated with mixed layer processes and different dynamics controlling it. So we would have expected that the real contrast was from the northern Bay of Bengal to the southern Bay of Bengal in terms of where eddy variability occurred. But we're not actually seeing that when we look at this 25 years of altimetry. Instead, what we're seeing is more of a east-west dipole, if you will, of eddy variability. So what we see is that the highest eddy radii, the highest eddy amplitude, are all going to be in the highest EKE, are all actually going to be in this EICC region where the western boundary current of the Bay of Bengal is. And perhaps that's not surprising given that it is a western boundary current, and those of course have the highest EKE values. So we are seeing the highest levels of eddy variability in the western Bay of Bengal. In the eastern Bay of Bengal, however, we actually have a lot more smaller eddies. We actually have more eddies being generated in this region. You can actually pretty much see where the Andaman Islands are, Andaman and Nicobar Islands are, just from where the number of eddies generated are. So we wanted to further explore basically what processes were controlling these large eddies in the EICC region. It should be noted, of course, that most of the eddies that are generated in this eastern Bay of Bengal area are going to be more topographically generated. So there have been previous studies that have looked into the role of Myanmar bump in generating eddies in this region. But we wanted to focus more on this EICC variability. So to do this, we took a multi-parameter approach, and that helped us to discern the difference between surface and subsurface eddies. So for those of you who are less familiar, surface and subsurface eddies are defined by where their PV anomalies are centered. So a subsurface intensified eddy will have its PV anomaly obviously below the surface, and you'll see doming of isopycnals both above and below that, which will create sort of the opposite SST response from what you would expect. And then a surface intensified PV anomaly will of course only have doming of isopycnals below the PV anomaly, and that'll have what you anticipate being the SST response being. And this allows us to use a multi-parameter approach to basically figure out which subsurface or surface intensified eddy structure we have, and then further analyze that. So we can see that here in our normalized radii eddy composites. So on the top here, we have all of our anticyclonic eddies, and the bottom we have all of our cyclonic eddies. To just sort of orient you a little bit, all of these are on a normalized eddy radii. So 0 is going to be the center, and then 1 normalized eddy radii, 2 normalized radii, etc. So what we see, and then we have our surface intensified, subsurface intensified, etc. So we have sea level anomalies. That's how our eddies are defined. Sea surface temperature, which just allows us to pick apart our surface intensified or subsurface intensified. And then we have OLR, which of course is going to be a proxy for atmospheric convection. And then ultimately precipitation, because that's really what we care about, is how these mesoscale eddies are impacting atmospheric variables and precipitation, specifically monsoon precipitation. So what we see is that we actually have a strong precipitation signal associated with the subsurface intensified anticyclonic eddies. And you're going, wait, but Heather, that means that it's a cold core eddy. Well, the thing is with the Bay of Bengal that a quote unquote cold core eddy is actually still probably above 80 degrees Fahrenheit, because the Bay of Bengal is a very, very warm basin. So even though it's a quote unquote cold core eddy, the cold core anomaly is about 0.3 degrees Celsius, and it's still a very warm eddy. So it's a cooler eddy, but still has about 2 millimeters a day more precipitation associated with it, with these anticyclonic eddies. The least amount of precipitation, which one might expect, is associated with surface intensified cyclonic eddies, which are your traditionally cold core eddies. They have significantly less precipitation associated with them than the other forms of eddies. So this is applied to all eddies in the Bay of Bengal overall. And we wanted to see, okay, how about years where we have suppressed eddy variability versus enhanced eddy variability? So to do this, we looked at Rossby wave propagation in the Bay of Bengal. So as I mentioned before, the ENSO and IOD phases are going to significantly impact coastal Kelvin wave propagation and Rossby wave propagation in the Bay of Bengal, specifically because, of course, ENSO and the IOD are going to impact those equatorial wind stress perturbations, which in turn really drive the strength of the Kelvin waves in the Indian Ocean. So we then parsed out basically corresponding El Nino positive IOD years, El Nino negative IOD years, La Nina positive IOD, and La Nina negative IOD, because these work together like cogs to either enhance or suppress the coastal Kelvin wave signal. So following a negative El Nino positive IOD year, you should have a suppressed Rossby wave response because you have a suppressed coastal Kelvin wave response. So you can see here that there's a much lower signal overall, and you have fewer eddies following it. On the other end of the spectrum, a La Nina negative IOD year should have a much higher coastal Kelvin wave response, and most higher should have a higher level of eddy variability associated with it, so more energetic, if you will. And this will also impact monsoon onset later on. So if you recall, because of the really strong IOD in 2019, we should have had a weaker 2020 onset, but because of the MJO and Amphan, we actually had an on-time monsoon and actually a strong monsoon. So what we then did is we looked at these eddy composites for an El Nino positive IOD year and La Nina negative IOD year. So starting with our suppressed phase, you can see that right off the bat, we have much weaker as mesoscale eddies and much less precipitation associated with them. So you can see our OLR values overall are much lower, and our precipitation values are fairly low overall. By contrast, our La Nina negative IOD year and much higher precipitation values associated with it, much stronger eddies associated with it. So actually, this is going to be following that. So if La Nina negative IOD year is in year 1, then year 2 is going to have this really strong response associated with it. So it's really important that we capture this mesoscale eddy field, and these really accurately predict the timing and strength of these coastal Kelvin waves in the Bay of Bengal, because that'll impact not only the mesoscale eddy field and the precipitation associated with it for the following monsoon system, but also can have impacts on freshwater transport and the following monsoon onset. So it's really important that we really accurately capture and monitor these systems. So in summary, satellite altimetry and salinity are both really useful tools to monitor and forecast the southwest monsoon, especially since everything is so connected. The freshwater fluxes, planetary waves, barrier layer development, and mesoscale eddies are all really important to track, especially with multiple parameters. And including these in not only forecasts, but in modeling efforts, we can really improve, therefore, our forecasts and monitoring of these events. Salinity and temperature variations that impact the spatial density field and mixed layer during ISO propagation are really important, not just for research purposes and for our own interest, but it can also impact biological productivity in fisheries in these regions. So it's really important also that we monitor and forecast these accurately. For my current research, multiparameter eddy tracking can be used to monitor not only air sea interactions, but also marine ecosystem dynamics. So that's where all my current research is, and that's sort of a passion of mine at the moment. And then of course, the real broader impact that everything has to go back to is that over 1 billion people are directly impacted, not just by monsoon rainfall, but their well-being overall is really impacted by these monsoons. So it impacts not just their daily lives, but agriculture, global and local economics, fishing routes, fisheries, shipping routes, their well-being, national security. So it's really important, just going back to the human factor, that we really monitor these systems and forecast them accurately over time. So finally, I would like to acknowledge my many sources of funding, and also the work of my co-authors, Dr. VSN Murty from the NIO, Dr. Subra Balusu, my PhD advisor, and Dr. Corinne Trott, who was in the same lab as me and is now at NRL. And then, of course, my sources of funding, where the asterisks at the bottom are my current sources of funding. Thank you all for coming today, and I'll be happy to take any questions.
Great, thanks, Heather, so much for that really nice talk. We do have time for some questions. You can either type your questions in the chat or raise your hand using the reactions button at the bottom of the Zoom screen. And I see we have a question from Jerry. Go ahead.
Hi, Heather. Thanks. Very nice, interesting talk. I just had two questions for you, actually. One is, can you get a monsoon onset without a monsoon onset vortex? And the second question would be, you were talking about onset at Kerala, and then you're kind of using that interchangeably with monsoon strength, but is there a relationship between the date of monsoon onset at Kerala and the ultimate season average monsoon strength?
Yes. So to answer your first question, yes, it's possible to have monsoon onset without a vortex. It's about, I want to say, I could be wrong on this statistic. I want to say about like half the years don't actually have a monsoon onset vortex. You do still have that enhanced precipitation over Kerala leading to monsoon onset. You just might not have that sort of mesocyclone that propagates through. So some years have it, some years don't. That's not my immediate field of study, but it does definitely vary from year to year. And I know I've been using sort of onset and strength interchangeably a little bit. So there is, so the strength of onset can sometimes impact the strength of the monsoon overall. So the strength of the monsoon overall is the sum total of the precipitation from June 1st through September 30th. So that's sort of how they characterize it. And that's where your active and break phases in the monsoon really occur. In terms of the strength of monsoon onset, that's a totally different thing. And that has to do with how strong your Arabian Sea mini warm pool is. At least the conventional wisdom is the stronger your Arabian Sea mini warm pool. So right here pretty much is where the Arabian Sea mini warm pool is. And that can exceed temperatures of like 31 degrees Celsius. That's an extension of the overall warm pool that's already in this region. So it's a mini intense warm pool there. And sort of the extent of that warm pool in theory contributes to the strength of monsoon onset. Basically the active phases associated with that, if that makes any sense.
Okay, yeah, thanks.
Great. We have a question from Joe in the chat. I'll read that out loud. Can an accurate 2 season ahead forecast be made using the October state of the Bay of Bengal?
So you mean, so 2 seasons ahead, do you mean like if you're looking at October of 2019, can you predict the monsoon of 2020 or 2021?
Joe, do you want to unmute and clarify?
Yeah, so I'm thinking 2019 could predict 2020 monsoon strength or something like that. Have you looked into what the predictive skill associated with the Kelvin wave in the Bay of Bengal or the eddy activity in the Bay of Bengal?
So I think you could make a decent climatological forecast. So I'm more of a satellite person. I'm not much of a modeler, I'll admit that. I think you can make a decent climatological forecast that way. But actually 2019 and 2020 is a good example of that, because all of our 2019 predictions, all of the setup with the really, really strong IOD that we had in the Mesoscale eddy field being what it was, we should have had a delayed onset and we should have had a weak monsoon associated with the 2020 monsoon. But the combination of MJO activity and Amphan happening actually allowed for the monsoon to onset with climatology. So that was already sort of out the window for our conventional IOD ENSO wisdom with how the monsoon onsets. And then of course it was almost a strong monsoon. So I think it's better than just guessing whether it'll be a strong monsoon, but I wouldn't say it's, at least on my end, it's not very cut or dry whether or not the October state 100% dictates the ensuing monsoon strength. But again, I'm not a modeler.
But I would agree. I mean, I think that I was thinking of this as just a statistical model, and it's not going to be a perfect statistical model to predict monsoon strength, but it might have some predictive skill.
Yeah, so sort of in a composite idealized scenario, it would contribute. Yeah, I agree.
Other questions? I have a question, Heather, about the first part of your talk about the relationship that you kind of looked at with ocean heat content. Do you foresee this in the future impacting monsoons as we expect the oceans to continue warming? Do you have any thoughts about future changes in monsoons?
Yeah, actually, so there's been a decent amount of research that's gone into this. The short answer is that we're not sure how climate change and changing ocean heat content is going to impact monsoon strength. The long answer is that basically the increasing sea surface temperatures are actually increasing the temperature gradient between continental India and the surrounding ocean. So that temperature gradient is increasing. So from that point of view, you should have a stronger monsoon, because the monsoon, you can think the southwest monsoon you can sort of think of as a really large land sea. You can think of as a really large sea breeze type situation. So from that point of view, you should have a stronger monsoon. However, the Indian Ocean dipole is actually going to be sort of shifting statistically closer towards a positive Indian Ocean dipole, just because of the way the temperature gradient is happening. So you're actually going to see more positive IODs moving forward, just because the mean state of the ocean is going to be shifting towards that. And a positive IOD should, in theory, again, lead towards a weaker monsoon overall and a weaker, it's more like an El Nino type. It acts more like an El Nino in the Indian Ocean. So it suppresses monsoon onset and suppresses the coastal Kelvin wave, the equatorial and coastal Kelvin wave signal associated with that. So then from my mesoscale eddies, you should have fewer mesoscale eddies and weaker precipitation. So I think it's going to be highly regionally dependent and depending on a great many factors. But it's definitely going to be really interesting moving forward how all of these different moving parts associated with monsoon strength are going to work together or work against one another to impact the monsoon moving forward.
Great. Yeah, thanks. Well, I think we'll end there. We're at the top of the hour. Thanks very much, Heather. Next week, we have Precious Monway from CGD presenting.